Now what is rotation? In case of rotation, the object always keeps fixed distance from a particular point. If this fixed point is origin, say for example, then if any point on the object is here, say P, initially at xy position, so the positions, new positions will be such that, say P dashed, such that it will always keep the fixed distance, same distance from the center of rotations, from the pivot point or center of rotation. So this is the direction, okay, that direction is specified by that angle theta. That means the object is rotated through an angle theta, in this case anti-clockwise, keeping fixed distance r from this center of rotation. Let us consider that the positions of the new object is at P dashed, whose coordinate is x dashed, y dashed, and the angle of rotation is theta, and here the angle is measured following the normal convention, that is, if the angle is anti-clockwise direction, it is considered as positive. If the angle of rotation is in clockwise direction, then it is negative. So this convention is used here. Now let us try to obtain the transformation equations for pure rotation. We can write that the original object point P is represented by r phi. Let phi is the angle with the x axis. So the polar coordinate for P is r phi. So we can say x is equal to r cos phi and y is equal to r sin phi. So what is x dashed? This is x dashed. So x dashed is same, r is the distance from origin. So this is r and angle is theta plus phi. So we can write x dash is equal to r cos theta plus phi and y dash is equal to r sin theta plus phi. Okay. Now our objective is to express the new positions P dashed in terms of known quantities, so that we can get the transform points after the transformation in terms of the known quantities. In this case, what are the known quantities? Initial point, object point x, y, and the angle of rotations. So we have to express this P x dash y dash in terms of x, y and theta. That is my objective. So we can write x dash as r cos theta cos phi minus r sin theta sin phi, and we can write y dash is equal to r sin theta cos phi plus r cos theta sin phi. Now you can substitute this r cos phi as x. So we can write x dash is equal to this r cos phi is x. So this is x cos theta minus and r sin phi is y, that is y sin theta, and y dash is r cos phi. Here r cos phi is x, so this is x sin theta plus y cos theta. So these are the transformation equations, transformation equation for rotation. Now again, how this can be represented in matrix form. Why matrix form is used, we will come to that point, but let us first see how we can represent this transformation equation in matrix equation, matrix form. So we can write left hand side of this is x dash y dash column matrix corresponding to P dash, which is equal to, here we cannot express this transformation equation in terms of two matrix addition, because here the equations are coupled equation, x and y are coupled. So we have to have some operator matrix operated on, multiplied on xy. So which will be this matrix, so that if we multiply these two, these transformation equations will be obtained. So this must be cos theta minus sin theta. So cos theta into x, that is x cos theta, minus y sin theta into y, that is y sin theta. So these equations will be obtained. And what will be this rho, so that this multiplied by this will give you this equation. So this must be sin theta into x, and this is sin theta, and this is cos theta. So left hand side, this is P dash, which is equal to, this is some operator, we are calling this operator as rotation operator R, with respect to the origin, because origin is the center of rotation, through an angle theta, and this is multiplied on the object point, this is corresponding to P, operated on P. So we can write these transformation equations in terms of matrix operations as a single matrix equation as P dash is equal to R0 theta operated on P. Now let us first consider why we are interested for representing these equations in matrix form. First of all, if we represent everything in matrix form, matrix is nothing but a two-dimensional array. So it can be easily represented using any programming language, because almost all programming language supports array. It is two-dimensional array. And the operations are also very simple, because in this case you require to multiply two matrices, and in earlier cases, in case of translation, we require to add two matrices. So these operations are very simple and very fast. So this is the pure translation operation. Now we will concentrate on the next operations called scaling. Basically, scaling will change the size of the object without not necessarily changing the shape of the object, because in this case, suppose we have a rectangle of this size. We want to increase the shape of the object. We want to enlarge this object, keeping that center, this is center, which is the intersection of these two diagonals, keeping this center fixed. So in that case, what happens if we try to enlarge it? Then the shape will be something like this. In this case, the size is enlarged, but after the transformation, the rectangle remains rectangle. Or it may happen that if the amount of change along y and amount of change along x are different, then it may happen that this rectangle is changed to square. So in case of scaling, both are possible. So here we cannot say this is purely rigid body object, because in earlier cases like translation and rotation, the only position of the object changes, but there is no change of the shape or size. But in this case, the object is scaled up or scaled down, maybe uniformly or maybe differentially, non-uniformly. Both are possible. And there are many applications where the combination of all these operations are required. For example, suppose I want to simulate a situations in an applications where a car is moving or a ball is thrown. So, from the viewing positions, if we see that the object as it is going far from the viewing positions, so its shapes diminishes. So, in that case, how we will simulate this situation? So, in that case, we will draw different shapes of the object at different positions, and then all these shapes are played one after another sequentially. So, this will simulate animate the situations like this ball is moving along this animation path. So, this type of situations can be created with the help of the softwares, and for these softwares these primitive operations are required. So, in that case the combinations of change of positions as well as the change of size both are required. So, real applications require the combination of all these things. Now, let us see how we can represent scaling operations. So, in case of scaling, again we are considering any arbitrary point P on the object. Okay. So, from the definition of scaling, if P is changed to, suppose this is P and this is P dash. So, P dash is x dash y dash and P is x y. So, in this case P is change its positions to P dash such that x changes to x dash, y changes to y dash, and the ratio of this change, that is final x amount x divided by original x, this ratio is called the scale factor along x direction. In the same way, y dash by y, that is the scale factor along y direction, that is sy. So, this is scaling along x direction, because the amount of scaling, it can be scale up or scale down, is the final x extent divided by original x extent. This ratio is the scale factor along x direction, and in the same way final y extent by final initial y extent is the scale factor along y directions. So, we can write the transformation equations from this as x dash is equal to sx into x and y dash is equal to sy into y. So, these are the transformation equations for scale. If sx is equal to sy, that means scaling along x direction is same as the scale factor along y direction, that is called uniform scaling. That means in that case the rectangle remains rectangle, square remains square, a circle if scaled up that remains circle, but if sx is not equal to sy, that is scale factor along x direction is not equal to the scale factor along y direction, that is called differential scaling. Or non-uniform scaling. This is basically non-uniform scaling. So, in that case the size of the object changes as well as shape of the object also changes. Like if this is the initial object, after scaling it may happen that it becomes an ellipse. Initially it was rectangle, after scaling it may happen it is a square. So, in that case size is changing as well as shape is changing. So far we have discussed these three pure operations: translation, rotation and scaling. Besides these three, there are another two basic operations or primitive operations. These are reflection, mirror reflection and shear. We will discuss those things afterwards, but before that let us introduce another very important concept, that is, in case of translations we have discussed that some matrix is added with the initial point, and in case of rotation and scaling some matrix is multiplied, because here in case of rotation r0 theta is multiplied with the object point, in case of scaling here, these are the scaling equations. So, here also the matrix is multiplied, because we can write in matrix form here x dash y dash, which is equal to some matrix operated on object point x y. So, this will be s x 0 0 s y. So, this is nothing but the scaling matrix S with respect to origin, or we can say this center, or say this center is say O. So, O, if this is the center of the coordinate system, and with respect to the scale factor Sx and Sy operated on P. So, here also this operator is multiplied on this object point to get the transform point P dash. So, in general we can write these sort of transformation equations as, if P dash is the final point, and if you apply all these operations in combinations, then we can write P dash is equal to some matrix M1 operated on P plus some matrix M2. Now, it is very clear from this discussion that this addition term is due to translation, and this M1 is due to rotation or scaling. So, if there are more than one operations like first scaling followed by rotation then translation, then we require to multiply the rotation scaling matrix with the object point. We require to calculate the new positions due to the scaling. Then we have to apply the rotation corresponding to that another matrix is multiplied, and then some matrix will be added corresponding to the translation to obtain the final position. So, in this case we need to calculate the intermediate positions separately, and if we want to get back the original positions, then we have to perform the inverse operation. So, this creates a lot of computational time, because we require to calculate the intermediate positions, and accordingly the inverse transformations will be performed. So, to avoid this kind of situations, if we can represent every operations in terms of matrix multiplication, then getting the inverse operator, and that is a separate matrix. So, we can represent every operations in terms of matrix multiplication. So, the operations will be done in a pipeline, in a chain of matrices, chain of matrix multiplication, and all these operations will be performed in succession, and their inverse operations will also be performed in succession. So, that is requiring another a slight change of the representations of the coordinate points in terms of a new coordinate system called homogeneous coordinate system. And this concept of homogeneous coordinate systems is required because there is no homogeneity in the representation of these operations. Like in case of translation, we have represented the operations in terms of matrix addition. In case of scaling or in case of rotations, we require matrix multiplication. So, there is no homogeneity in the operations, and to make all the operations in terms of the single multiplication operations, we need to introduce a new coordinate system known as homogeneous coordinate system. Homogeneous coordinate system, because we need to introduce homogeneity in the operations. The advantage is twofold, that is, we can perform any operations or its inverse just in a chain of matrix multiplications, and we need not require to calculate intermediate positions. So, it will be efficient in terms of getting the final positions, okay, in less computational time. That we will discuss, we will consider in next session.